Okay, welcome everybody to this session about performance monitoring. There will be 3 people saying something about this subject. I think a lot of performance monitoring has been done in the past, of course, and we still have to do that a lot in the future. But we are looking a little bit here at methodologies, how we can make end-to-end performance monitoring possible. A lot is done in NRENs and local networks, but never really looking at the user perspective that there is an end-to-end issue. So there are lots of initiatives about that, and at least we have 2 of them here who look at such an infrastructure. That's Eric Boyd, who is already sitting there, and he will talk about the Internet 2 pipes initiative. And after that, Nicolas Simar will give information what HEAnet is going to do concerning the help towards users when they have an issue, not only with the network but also with other things. That are the infrastructures, but you need, of course, more. You still need methods of measuring things and performance. And Sven Ubek from will present something about how to do that in high-speed networks. So that are the 3 talks of today. But we start with Eric Boyd, who is looking after the pipes projects in America for Internet 2, and furthermore he's active or co-chair even of the GGF network management working group. So I would say, Eric, the floor is yours. Thank you. You have to press the green button.
Thank you very much. So, as Victor said, I'm Eric Boyd with Internet 2. Work on the end-to-end performance initiative, which is an ongoing effort of several years at Internet 2. It includes both in-house staff and volunteers from the Internet 2 member community and elsewhere. And so a lot of the work I'll be talking about is work done there. Some of the slides are put together by Guy Alms, who's in the audience, and Matt Zakakis. And some of the people who've been working on this include Jeff Boot, Rich Carlson, Prasad Kalyam, and many others I've probably forgotten. So mistakes are mine, credit to them. So let me tell you a little bit about the PIPES project. I'm going to have a tiny bit of introduction here, but I'm going to try to move beyond that pretty quickly, as I talked a little bit about some of this a year ago in Croatia remotely. But I think we've made some significant progress since then, so that's what I'm going to focus on. But basically, so the PIPES project is what we call the Performance Initiative Performance Environment System. And yes, we came up with the acronym first. The idea is sort of to think of end-to-end performance as a pipeline that you'd like to split up into different components and be able to do partial path analysis. I really do want to emphasize the collaborative nature of this project. We're trying to combine the best work of many organizations. There's people in the audience from many of these here, including Dante Gian, Daresbury, the EGEE, the GGF Network Measurement Working Group, Leonard Gast, the University College London, Peter Clark's group, some folks at Georgia Tech, and the like. So I'm sure I've missed some, but we are trying to stitch together a lot of different efforts here. So got 4 goals here, and if you saw this talk a year ago, you would have only seen the first bullet point as the goal. The others have sort of evolved over time. But basically what we're trying to do is a couple different things. On one hand, we'd like the end user of some degree of sophistication, let's leave that vague, to basically be able to say, I think I have an end-to-end performance problem, but I don't want to go through the whole rigmarole of calling my local system administrator. I don't know how to prove it to him or her. And then when I finally do, they redirect me to someone else. And then sort of by that time, the problem's gone away. What we'd like them is to be able to quickly and easily say, this is where the best place to start looking for the performance problem is. Here's some proof to convince a system administrator I do know what I'm talking about. And I can contact them right away. Sort of out of that initial goal has evolved a couple others. we sort of have this idea that it would be nice to, if a sort of super traceroute tool existed, that you could basically say, what are all the intermediate nodes between this end and that end? And wouldn't it be great if I could have a measurement node next to each router along the path? I had root access to it. It already had installed all the tools I might want to run. Had a data collection set up to dump the data into a nice database with analysis software. And oh yeah, the tests that I might want to run are usually, or they've already been run for me, so effectively zero time. So that sort of far-off vision is actually what we think we can get pretty close to, and that's what we're working towards. We really want to make partial path performance data publicly available. Limited write access, but pretty much untrammeled read access to active measurement test data. Both encourages the people providing the service to do a good job and makes it easier to say, no, it's not the network, it really is your end host, to sort of contradict that question. And last but not least, many members of the Internet 2 membership and in Europe elsewhere, they cross international boundaries all the time with their end-to-end paths. And so we don't believe that everybody's magically going to adopt our system. So what we want to do is make ours interoperable with other groups, and through that allow people to diagnose and performance problems across multiple administrative domains and through multiple measurement frameworks. And the work in GGF is along those lines. So what it might look like is if you have an end-to-end path across the top, and this is sort of one chunk out of that end-to-end path, is you have an associated measurement node next to each router. You may have regularly scheduled tests or on-demand tests that you can request from a third-party system like your laptop. Those results are archived. You can request test results and get them back. So if you imagine this sort of stretched along the whole end-to-end path, that's what you might get. So a sample deployment might look like this. This is sort of one half, sort of the left half in the middle, but not the right half. But basically, if you have some regional nodes, which in Europe might be, sort of the DMZ for an NREN or something like that, and then you have backbone nodes, which might be sort of next to the various HEAnet routers. You could have regularly scheduled tests. You could have both in either sort of like, the French domain or the HEAnet domain, and you could store that data in various databases, or sort of orthogonal to all that, maybe you're members of the HENP, the High Energy Nuclear Physics community, and you care about a certain set of machines that sort of cross multiple measurement domains. You'd like to be able to run regularly scheduled tests between them and store that data sort of orthogonal to the administrative boundaries. So this is sort of a sample of how you might deploy this. So we went through an exercise recently, and this is sort of after the fact in some extent, but the project is sort of breaking down into 3 phases, and I'd say we are pretty much done with phase 1, at least as we initially envision it. Phase 2 is well underway, and phase 3 is still sort of out there. Phase 1, basically what we're doing is we've been creating tool beacons, and I know beacon can be used a lot of different ways. Another daemon might be a better word, but basically the tool is up and running. It's governed by policy limits and policy constraints and limitations set by the owner of the administrative domain, but then anybody can sort of test to it within those constraints. So imagine today somebody wants to do an iPerf test into your network. Either they send you an email and you say, sure, you can have login access onto one of my machines, which you probably are unwilling to do, or sure, I'd be willing to get up at 2 in the morning and kick off that iPerf server for you because that's the time you need to run your test. So what you might do with BWCTL, for instance, which is a resource allocation broker for iPerf, is you just leave that up and running all the time. You say, you set different policies, like this class of user I'd like to be able to allow to run this test, this class to run this test. You may or may not put a key on it, which you have to basically, someone would just request a key in advance. But then the tool itself takes care of all the scheduling for you, so you don't have to worry about 2 tests running at the same time that might pollute each other's data, and you don't really have to give away, the keys to the whole kingdom for a very limited test. So We've got those beacons written and released. There's some web pages there. You can download them. They've got documentation. You can install them, and then people could run a one-way test to you, or they could run a iPerf test to you if you had that up and running. And I'll go into those tools a little bit more later. We also sort of what I call the glue. Here I call it the measurement domain support, but basically the software that allows you to run a bunch of tests on a regular basis, gather that data up, put it into a database. There's a lot of sort of subtle performance requirements in terms of when should you aggregate the data, when should you throw it away, should it be on the clients or on the database server, that sort of thing. It takes care of all that. And then some of the visualizations, some crude CGIs that allow you to sort of mine the data and pick up trends. And I'll show you some examples of those later. We have that working. We have that deployed on Abilene. And we've deployed it a couple more times for several demos, which I'll talk about. And we are actively working to sort of incorporate the changes we've noticed we needed and make that product worthy and put it out in the next number of months. Phase 3 is more federation support. This is the area we sort of waved at but haven't gotten very far in. And when I talk later about outreach to other communities, these are areas we could really use a lot of help on. We need real, if we're going to build these federations of measurement domains and federations of measurement infrastructures, we need much better authentication and authorization. You know, basically I'd like it so that a network engineer at the French network could be identified by that network as a trusted network engineer. And I could say, all right, well, I'm, you know, Abilene's network engineer, and I trust them to identify the right person, so anybody in that role can do the following things. So that's one area. Second is discovery. The way you'd like it to work is sort of if you bring up an OAMP or a BWCTL beacon, it sort of self-registers and announces itself to the world, and anybody else who wants to do that super trace route can magically discover it. And you can also find the database that the regularly scheduled test data already exists in. So we're just barely scratching the surface, and that's sort of a big unanswered question that a lot of different groups have said, yeah, somebody needs to do that. So I think a couple people have started a little bit, but we could use a lot of work. And third is making the data available. We don't just want to make the data available via our proprietary web pages. You know, we want lots of different groups out there to write analysis software, and that analysis software to be able to read data from multiple different measurement domains and come up with interesting syntheses. So there's two already that I know of. There's the NLAN DAST Advisor project, and there's the Mona Lisa project. And both of them can read our data now. They can read data from other measurement systems as well, such as AMP and the Slack work, and they can display it. So what we're sort of, you know, there's the test collectors, and there's the data collectors, and then there's the data analyzers. And sort of if you think of that as an X, at the cross point, that's where the GGF Network Measurement Working Group schemas are, as a way to, in a common format, request data or request tests and then get results back. So I'm just going to kind of go through these quickly. You can read about them on the web. BWCTL is a wrapper for iPerf. iPerf was produced by NLAN DAST. It's a well-known tool for measuring, like, you know, TCP throughput. Basically, the BWCTL is a resource allocation broker. iPerf was not really designed to be set up in a mesh of regularly scheduled tests between like 11 nodes by 10 nodes, so to speak, like we have in Abilene. This covers for some of those problems that it wasn't designed for. Basically, you don't want two iPerf tests coming in at once through the same NIC card, because that's a resource constraint. You don't want to pollute each other, and a lot of different other things. So this has all that. OAMP is a reference implementation of the OAMP protocol, one-way delay. It allows you to basically set up one-way latency tests, and you can read about that on the web as well. NDT is a tool Rich Carlson's been developing in a couple different organizations. I think he did most of the work at Argonne. He's now working with us. The network diagnostic tester. Basically, a lot of the other stuff I'm talking about covers what I would call the middle. If you segment the end-to-end path into the first mile, which is sort of my laptop to sort of the first router, where there's a performance measurement node next to it, and then there's the whole middle, and then at the very end there's the last router with a performance measurement node, and, you know, a server at the other end or a laptop at the other end. You don't really have many people are not going to have, say, half of iPerf installed on their laptop, on their Windows laptop. So what this does is this looks at the first mile. Basically, you go to a well-known NDT server. It redirects you back to the closest NDT server, which hopefully would maybe be installed at your campus DMZ. And then it has a couple of custom tests. You basically download a Java applet, and it runs a bunch of custom tests, and it looks for sort of what we would call the top 10 most likely performance problems, whether it be duplex mismatch or whatever. So that sort of is how our answer to the first mile, with the rest of the stuff being how to diagnose the middle part. So where's pipes deployed today? So the circles are sort of the beacons I was talking about before, and there are other people who have downloaded the tools. They're open source and available on the net, but these are the ones I've sort of been tracking and pushing. The red circles are Abilene. There's 11 nodes in Abilene. There's actually 4 measurement nodes next to each one of them, and the red lines indicate the fact that we've got the measurement glue sort of up and running for them as well. We've been pushing on a couple of our universities that have a close relationship with Internet 2 as technology evaluation centers, NC State, Ohio, and San Diego, and they've got OAMP and BWCTL boxes up. We've also been working with some government labs, including LBL and soon Fermi and Brookhaven, and trying to get beacons up and running there as well. We've also worked with the University of Hawaii for a demo last winter. In Asia and APAN, there's been a commitment to put some boxes together, and I hope I have this right in terms of what's in progress and what's not, but the idea is basically to get 3 BWCTL boxes up, 2 in Japan and 1 in Korea. And I've been working very closely with Nicola, who will talk next. And if I understand the plan correctly for HEAnet, they will be evaluating OAMP and possibly BWCTL in the next month. And we've got some of the boxes already installed, at least the London one. But there will also be boxes put in France, in Frankfurt, in Poland, in Italy and Israel, and CERN has already had some temporary boxes put at CERN. I think we need to replace them with some permanent ones, though, as well. So those are sort of the footprint today. So these are tests, or these are machines that you could apply to have a key if a key is necessary and actually run a test to. So if they matched up with your end-to-end path, that would be very useful. So I'm going to try to spend the bulk of the time, not too much time, on pipes use cases. And this came out of some discussions with Guy, although I don't know if he'd agree with all the things that I put up here. But there's sort of different ways you could use this sort of software. You could do edge to middle. So if I have a laptop and let's say I'm at a U.S. university, I want to test to Abilene, or I want to test an end-to-end path that goes from one university to another. So halfway through that path is Abilene. So it would be nice if I could run sort of an iPerf test or a one-way latency test from me to Abilene, and that would let me know, is it in the first half or the second half? So it's sort of the first case of the partial path analysis on demand. And that exists today. You can get these URLs off the slides later. But we basically allow open OAMP testing to any Abilene node, and there's a web page that displays that. And we have limits on BWCTL, only that we got to watch the load on some of our machines a little bit. But basically, behind the scenes, if you fill out this web form, Matt, our network engineer, will give you a key, and then you can run iPerf tests to Abilene as well, subject to the constraints of the limits and policy files that we set up. And the idea is basically any other administrative domain could set them up what was appropriate for it. So this is just an example. Middle to middle, sort of regularly scheduled tests. There's sort of 2 uses for this. One might be sort of raw data for third-party analysis tools, and I've given a link actually to the Mona Lisa tool and show it consuming our pipes data plus the Indiana Knox weather map data, and you can look at that. Also for sort of quality control of network infrastructure, how good is Abilene on a regular basis, and do we respond when Abilene falls down a little bit? So I'll come back to these other 2, but I'm going to delve into that one for a little bit. So the Abilene measurement domain is part of the Abilene Observatory. That's the URL. It has regularly scheduled OAMP and BWCTL tests, and there's a bunch of different web pages here that you can look at that show the latest results, sort of a weather map, and what we would call our worst 10 performing links, and I'll talk about that later. The data is also available via web service, and that's what tools like Advisor and Mona Lisa use. So quality of control of Abilene. So basically our approach is a problem-solving one. We use the ongoing measurements to sort of flag a problem, and we use ad hoc measurements then to really dig into it. So we are aiming for gigabit per second flows on Abilene of iPerf TCP. We use a stock TCP stack, but then we've tuned it, obviously. It's very sensitive to loss, and it sort of acts as our canary in the coal mine. And we're supplementing that soon with Web 100 as well. And you do have to watch out when you see a bad result, because the answer could be there's a problem with the measurement infrastructure, or there's a problem with the network. It's just because you see a problem doesn't mean it's always the network. It could be with the measurement infrastructure. And as we go through multiple iterations, we'll get better at that. But you know, it does help. So, like I said, we have regularly scheduled tests. One of the things we observed that's particularly important is sort of what were the worst 10 TCP flows in the last 24 hours. Between every pair of Abilene nodes, we do a iPerf TCP flow every hour. So that's, you know, like 24 of them. And then we say what were the worst 10 of any of those 110 node pairs. What was the first percentile, what was the 50th percentile, and what percentile broke the 900 megabits per second threshold. General conclusions, I'll sort of show you some examples of that. IPv4 and IPv6 to date seem statistically indistinguishable, although we haven't done a rigorous analysis to prove that. And if you see consistently low values to one host or across one path, we have a problem. So this would be a very good day for Abilene. You'll notice that every single test, this is today's result actually, I think, or yesterday's, every single test crossed the not only 900 megabits per second, but 960 megabits per second. And we don't get that every day, but I mean, that's still pretty impressive to be able to do for 24 hours. The top 10 are all good, the first percentile is good, and the 50th percentile is 982. So what happens when it's not like that? So Guy started doing this by hand. And we actually got a script now that does it as well, but I'm just using his examples here. So this sort of starts in March of this year. The top line for the next several graphs will be consistent exactly there. The 50th percentile is rock solid. The blue line is the first percentile, and when you see the first percentile dip, that means something's usually going wrong. So in the middle of March, we had circuit problems along the West Coast, and they were pretty clearly identified. We see some recovery. Things become more stable, and then something started knocking our Seattle node. He fixed things somewhat, but got even worse, and we eventually diagnosed the problem as a Web 100 interaction. Things are going better, and then in the middle of May, we had a Junos upgrade that caused a lot of problems, inducing packet loss, and the 1 percentile fell precipitously, chiefly impacting long-distance paths. So basically, all the routers got new software. Everything seemed to come up, but on some links, the utilization didn't rebound. So the worst 10 reflected this, and it turned out to be a QoS parameter configuration format change. So this would be what the top 10 looked like on that day. Notice how low across the 900 megabits per second threshold came, and where the 1 percentile is. So then things got better. And then, not shown on those graphs, but we had another time when things sort of went down. I mean, this is not nearly as dramatic as before, but this is not that good either. And we figured out, once we noticed this, that streams over the Sunnyvale to Los Angeles link were showing problems. The NOC responded, and they found errors there. So we've now convinced our NOC to start tracking this a little more aggressively. Edge to edge. So I mentioned before application community. So one of them is the VLBI community. Basically, they'd like to do, they have multiple radio telescopes, and they'd like to simultaneously record the data, and then today they ship it. They'd like to be able to do it live. So David Lapsley, who works for Alan Whitney, did this. He set up BWCTL along his end-to-end path that went from Haystack to the Abilene node in Washington, D.C., across to Amsterdam, and then it goes up through London into Amsterdam, and I think it goes to NordUnet and then to SUNet. and then it goes to Ansvalla, Sweden. So his problem was the performance was not good enough to do what they wanted to do. No one had demonstrated this. So we gave him BWCTL. He was able to decompose the path, isolate the problem to local congestion in the haystack area. Hey, it wasn't the network, it was local. And they upgraded the bottlenecking link once they had proof that this was the problem. And the result was it was the first demonstration of real-time simultaneous correlation of data from two antennas. Now, the result isn't that good, so they're keeping working on it, but they did manage to do it. So in the future, they have a very heavily scheduled machine, so he wants to optimize the time of day for non-real-time data transfers, and they want to extend their BWCTL deployment to 3 more sites beyond the 3 they already have. One other quick example of an application community, we've been working with HEAnet. They've got 3 government labs, we have 3 universities. One of the things they noticed was a 400 microsecond one-way latency jump with the OAMP measurements, and it turns out that they were right on. The result looked like this. You can see the fairly significant jump. And what they detected was somebody plugged something in somewhere else. And the net effect of that was a 600-kilometer optical distance increase. So the OAMP measurements were sensitive enough to catch that. Other example use cases are sort of edge-to-campus DMZ. So coupled with those regularly scheduled middle-to-middle is using NDT, as I talked about earlier, to determine sort of where is the problem, is it local or not. So to wrap up here, I tried to overview what we're doing with pipes, and I tried to give you some use cases in terms of why this is useful and interesting. But we've been working very closely with the folks at Dante and at the various NRENs to increase our collaboration, because as you'll notice when Nicola gives his talks, there's a lot of overlap between what they want to do and what we want to do. So there's sort of 3 levels of interaction we could have. One is awareness of each other's ideas. That's good to know, but we can probably do better. 2 is that our measurement framework should be interoperable. Our important customers, researchers who have high network capacity needs, often cross international boundaries, whether it's VLBI or HENP or what. So at the bare minimum, they need to be interoperable. And to be honest, the easiest way to make them interoperable is to deploy something very similar, if not the same. So we're talking about, although we haven't committed, the possibility of actually working on this on shared tools and reconciling any differences in our architecture. We've made a lot of progress, but we still have a little ways to go. So some of the things we've done towards that end, we had a workshop last May organized by Peter Clark's group in University College London. That's where we sort of started sharing our architectures and reconciling them, and there's been a lot of change since then. Nicola and I and the folks at EGE put together a workshop in March where we got a lot of awareness of the 2 different efforts and a lot of talks, and you can review those talks at the web. The site I gave there. We've done a demo that spanned the U.S. and Canada and Europe, basically 3 different paths from Caltech to CERN. We did partial path analysis. I talked about the haystack to Ansala one, and I've mentioned that they're evaluating some of the pipe software as well. So this is my how can you participate wrap-up slide. So things you might be interested in doing is if you'd like to try out the tools, you're welcome to download them. They're all open source. They're all actually modified Berkeley license, which means you can do whatever you want with them. There's no limitations on them at all. If you'd like to set up a measurement domain, for now what we'd ask you to do is set up several beacons, sort of publicize them, decide what your administrative domain wants in terms of policy and limits, and set that up, and then register your beacons, which will mean putting them on a local web page that we link to, but eventually would mean using the software to sort of register them. So you're welcome to do this, and we encourage you to do so. And in the future, we'll be giving out the software to set up regularly scheduled tests. You could set up between any other people running such software that you were interested in. And then use it to solve problems and let us know how it's helpful so we can refine it. Questions?
Okay, thank you very much. Are there indeed questions? Oh, I have one perhaps to stimulate it. All the things you describe are looking at IP, layer 3, And yeah, there are also ideas set here that we are having to go to layer 1, layer 2, layer 0. What would you do there? Are you thinking about that, or do you want to wait until there is a, let's say, a good concept how to do it before going to lower layers? Or?
I don't know exactly how we'll do it. We did think about it a little bit. Wasn't including these slides, but people can review them later. When we did that Caltech Discern demo, one of the 3 paths that I meant, one of the paths was basically the default path, which is over Starlight Discern. One of them was sort of a cobbled together path that went through HEAnet Discern. The third one was a light path, and I won't define that, that was stitched together using Rick Summerhill's KIDS principle, keep it difficult, stupid, which is it wandered through Abilene and Canary, and that was a light path. And it was interesting because, you know, we basically could only put our nodes at the end. If you can see this diagram, you'll notice the red path is the light path, and we only have measurement nodes at either end. So it was difficult to tune the results. So, I mean, in a sense, what we were trying to show was how much more visibility we had. We got better results over the, now we didn't have a ton of time to tune, but we got better results over the black link, which was the default path, than we got over the light path, in part because we had the visibility. So we don't have an answer for you yet, but we have started, we at least tried to, in this example, demonstrate that there are things you're giving up, and we either need to solve them or realize that you're going to lose a lot of visibility.
Okay, thank you. Are there more questions? Here, over there.
Which traffic models do you use for the measurements? Are these just CBR streams which you're using, or
I'm sorry,
CBR streams for measuring the?
The measurements that we're making right now are OAMP, which is one-way latency test. It's a packet sent every second, a UDP packet sent every second. And for iPerf, we're measuring TCP and UDP just by invoking iPerf, which is sort of a standard in and of itself.
So you do not configure different kind of traffic models?
No, nothing at all, no.
Okay, I want to thank Erik for being here and having this interesting presentation. Thanks very much again.
And if you have questions later, just grab me and ask.
Okay, the second speaker will be Nicolas Simar. He's working in Dante and actively involved in, let's say, the ideas which exist on the European side to make something comparable and interworkable with pipes. But beside that, he is also looking at how to help end users. So that's more a human network than a technical network. And okay, Nicolas, the floor is yours to say something more about that.
Yeah. So unfortunately, as Erik announced, I won't be presenting the.
Do people hear him when he stands? Do people hear him when he stands up? Can you speak?
Yeah, I can speak. Do you hear me? Yeah. Okay. Thank you. Is it working now? So as Erik announced, I won't. Pardon? Still not working? That's better. Okay, it's a whole technique now. As Erik announced, I won't be presenting the performance monitoring initiative from Gen, but the Pert, which is the performance enhancement and response team. Basically, the Pert's origin comes from December 2002, at least for this version of the Pert, when and at that point of the time, historically. When you had a performance problem, most of the time you were pinpointing the wide area network. And in 2002, basically there were massive upgrades of capacity on the wide area networks. And since that time, we need to, when there's a performance problem between two end sides, you need to not only have a look to the wide area network, but you need also to have a look to the LAN, to the system, the application, and the hardware. So the problems are becoming much more complex to troubleshoot because there's not only the one which is a main cause of problem. So the generic end user who have to troubleshoot the problem is getting more and more complex and difficult for them to understand what the problem is and try to fix it. And that's on that ground that in December 2002, a group of NRN decided to meet and try to bring a kind of solution for those users. And basically, they met at Terena in Amsterdam, and we had there Mauro Campanella, Valentino Cavalli, Larry Dunn, Marianne Garcia, Simon Leinen, Victor Reijs, myself, Sven Bick, and Steve Williams. And from that meeting, they came up with the concept of a Pert, which is basically to provide a support structure to investigate where the problems are and to try to bring a solution to those problems for the end user. And it's not only having a look to the network side of things, but to have a look on for an application over computer networks. So the Pert will also have a look to what's happening in the end system and to the application. And the idea of the Pert was to have a structure comparable to the one of a CERT. So you can find a reference web page at the URL you can find there. The page doesn't have much information because we are still on a building up phase right now. So Pert stands for Performance Enhancement and Response Team, and it's a virtual team consisting of cross-disciplinary, I won't manage to say it, cross-disciplinary experts who can have a view across different types of technology and have a broad knowledge to try to pinpoint where the problem can be. And once they have located this problem, they can refer to the proper expert, which is a specialist in that area. Another goal is to try to come with some troubleshooting procedure and knowledge base in such a way that if a problem is recurrent, we can have some kind of cookbook or principles on how to solve it. And then the cross-disciplinary experts can then solve it without referring to the specialist. The Pert will also need some monitoring tools to help him troubleshooting where the problem is and locate where the performance degradation can come from. We need also a tracking system to store the tickets open, the additional information which comes related to this problem, and a knowledge base to document known performance issue, possible way of solving those problems, and also some successful diagnostic strategies. So with the experience of the Pert, we will be able to come with ways of troubleshooting the problem and approaching the various problems. And that would be made available on a website, basically. So what's the current status of the Pert? So basically, it's still very informal. So it's a group of people from various NRN which are putting some effort when they've got the available time for doing so. So currently, anybody can request the Pert to help them solving a problem. As this is still a pilot phase, the problems are solved or answered on a best effort basis. So don't expect to have your problem solved in 2 hours or 3 or 4 days. It's taking quite few weeks the time to have people starting investigating the problem, finding some different equipment to be able to run different tests, and so on. So it's taking quite some time currently, and we don't have also any dedicated monitoring tools, which doesn't help really to try to find out where the problem is. But we have got so far a roundup tracking system to help us to track the problem and have the opening ticket and everything which is following, all the different mail exchange which is following. So if you've got some performance problem, you can email us. We'll have a look to it. But as I mentioned previously, don't expect to have your request solved very quickly. But as there are not many issues which are being investigated by the Pert, we'll have a quick first look to what your problem is. Currently, we have two cases under investigation. The first case is between the Strasbourg Astrology Laboratory and Fermilab. So basically, they want to retrieve some data from Fermilab to Strasbourg. And basically, they only managed to have a 5 megabit per second transfer rate. So it's not really what they're expecting, and they're using AirSync. So the Pert has been contacted for that, and the first thought which occurred to the various people involved in the Pert, the first cause which could create this problem are an Ethernet interface not in a full duplex mode, some problem with the TCP buffer size, or some occasional losses over a long distance. It can also be some application problem or hardware problem. So it's very broad, the scope of things which can create some problem here. And so basically, as the machine on which those transfers were being done are operational, we could not use them to make some change and do some tests. So we had to find out some machines that we could use pretty close from where those machines were located. And so basically, we found out some machine close to Fermilab and another one within RENATER. And by just tuning the TCP buffer size and doing some memory-to-memory transfer, we managed to reach 90 megabit per second, which is an improvement from the 5 megabit per second. So here the strategy which is being used is to try to have a look to the problem small bits, bit by bit. So here we were trying to have a look from a machine to another machine over the network to see if it wasn't the network the problem. But as soon as they use AirSync with large buffer, the transfer rate drops to 20 megabit per second. So obviously there seems to have a problem in that area, and they are still investigating this problem. So they've got several tracks, and they need to eliminate one per one each of the potential cause of the problem. So that's where they are currently on that case. The second case is a case for the Jive community, where they. So Eric talked about that all the Jive data are sent to Dringerloo, where those data are correlated. And once those data has been correlated and stored, some researchers want to download the data. And basically here we have done a test to try to download the data from the Jive web server, and it's a 430 megabyte file. And there was some trouble to be able to download this information. So between Oxford and Dringerloo. And as they had some trouble internally within the Oxford side, we decided to start this download test from a workstation within Gian, and we use a Sun workstation and a Linux-based workstation. So the initial transfer, we were using HTTP, using wget, and it took 5 minutes to complete the 430 megabits per second, 430 megabyte transfer, sorry. So that's not really impressive. So a Pert case was opened there, and the two first potential causes which were being thought of were, again, the Ethernet interface not being in full duplex mode, and insufficient the TCP buffer not being large enough. So the first thing was to increase the TCP receive buffer size on the Gian side, and the results were much better than previously. So we reached 40 megabit per second. And then the second step was to increase the TX buffer on the Jive side. Unfortunately, the web server isn't as it is an operational machine. We could not change the TX buffer size there. So we used the Jive FTP server, and from there we managed to get 90 megabit per second. so which is an improvement from the 5 megabit per second. So we can ask the question there, is 90 megabit per second good enough? But I'm leaving the question open there. So what are the lessons learned so far? It's very important to solve the case to be able to identify the contact person at each end, to have technical information about the machines and is there firewall, what's the LAN topology, and blah, blah. We need also to find out what's the scope of the test which can be run. So we cannot do anything on operational machines. So we need to find pretty close to the end site some other machine on which we could run the test on. So there would be a recommendation to try to have some strong test machine that the Pert people could use when they have to troubleshoot problems. And those machines should be as close as possible from the end users. And the methodology which has been found so far is to try to minimize the amount of variables you are analyzing at the same time. So by doing some memory-to-memory transfer test, you are eliminating some part of the variables you need to investigate, and then you have a look to the problem bit by bit. So which are the next steps for the Pert? So as part of GN2, there will be a service activity, number 3, which scope is to enable end-to-end quality of service across European academic networks. And this, as part of this activity, the Pert will be an activity of this. So SA3 will be developing a provisioning system for Premium IP, and will also ask the anyone involved there to deploy a performance monitoring infrastructure as being defined by the GRA1, which is the Joint Research Activity 1 of the Gen2 project, which is a project fairly similar to what Eric has described in the previous presentation. Gen2 will, SA3 will be working on end-to-end QoS, or rather edge-to-edge QoS on the networks, which means that if a problem occurs, we can find out fairly easily what is happening on the network thanks to the measurement infrastructure which would be deployed, but nothing is said about what's happening between the end system and the edge of the network, and that's where the Pert structure will step in for quality of service problem, but also for other problems, not restrictively for the quality of service. So the milestone of the first 12 months for the Pert will be the establishment of the Pert, the deployment of a trouble ticketing system, establish the first troubleshooting procedures, and have a knowledge database available, and a first user guide by the end of the first year. There are different work items which will work on this Pert activity. So within SA3, they will have the work item 2, which is the definition of and the establishment of the Pert, which will take as input the experience we have gained within this year and within the framework of the GN1 project. So the case where that are being troubleshoot now will be a very useful input for the GN2 definition of the Pert. They will also have the delivery of a Pert documentation. So what are the most frequently seen cases, what are the procedures to troubleshoot it, and what are the best practice guide to troubleshoot it, and how are the different cases, how have they been solved. The work item 4, it's the Pert trouble ticketing system. So within GN2, anybody won't be able to open a Pert ticket. The end user will have to go through their NRN NOCs, and the NRN NOCs will open the case to the Pert themselves. So what will trigger a Pert ticket would be a ticket coming from a NOC, basically, an NRN NOC. They will also provide some Pert troubleshooting procedures, and they will set up the Pert day-to-day operations, and this will be based on 2 case managers, or at least at first 1 case manager, which is the cross-disciplinary expert, which will be funded by GN2 to receive case, open the tickets, and run the first batch of analysis to try to find out where the problem is. Then once he has isolated the problem, he will ask for a subject expert to have a closer look to what's happening. And basically those subject experts will be on a voluntary basis. So that's an outline of the Pert, where it's coming from, where we are currently, and what are the next steps of GN2. If you've got any question, feel free to ask them.
Thank you very much, Nicolas. If there are questions, let them flow. Not yet, no. How do you foresee? I think the Pert, you say it's like the CERT, and the CERT is quite efficient, where it works in a good way. I think everybody sees there the advantage of it. How do you see the Pert in the future? Do you think it is easy to get such a structure operational and running, or do you foresee problems, or is it just as simple as a CERT, although it also took a few years?
I don't really know how easy it will be, but basically the embryo will be 1 or 2 person working and opening case, and then relaying the problem to expert across different NRNs. So that's where I think the problem will be. The cross-disciplinary expert will be difficult to find, but they will be funded, so we can find them. But the expertise in different fields, those will be basically people working on some other topic that will bring into a problem. And I think that's where the whole challenge of the Pert will be.
Okay.
But hopefully, if the Pert has a very high profile for the various NRN, I think it's important to provide that kind of support for their users. I think that will be much more easier to set up.
Okay. I think you also need, like in the CERT, not only the NRNs, but also perhaps the application, the industry, the Microsofts who make the software and so on, and the hardware.
I think to be able to bring those guys within the group, we'll need to prove and to show that the Pert is useful. So as a first step, I foresee the Pert as being a kind of standalone organization within our GN environment and European Research Network environment. And when it has proved successful enough, we can start trying to bring other people on board.
Okay, thanks. Other questions? No? Okay, then I want to thank again Nicolas. The next presentation is perhaps the lower in the layer. It's more looking at the interfaces and how to measure things. And Sven, who is working for HEAnet in the research department, will look at aspects of high-speed performance measurements. Okay, go ahead, Sven. It's on the bottom. How do you call that? The blue. There, somewhere there. Yeah.
Okay. Good afternoon. My name is Sven Ubik. I am from HEAnet, and I would like to say something about performance monitoring of high-speed networks from NRN perspective, particularly about some possible issues which you may encounter. To give context to my talk, on this slide I tried to summarize my observations about backbone links in NRNs as for the traffic which is present on them based on the information which I managed to acquire. I think that most backbone NRN links have now installed capacity between 1 and 10 gigabits per second, and a typical long-term load on them is it ranges from 50 megabits per second to roughly 1.5 gigabits per second. And this fluctuates during the day from 1 to 5 on some links to almost nothing on other links, that is, some links have flat load. And the current optical links are of such good quality that they cause a very small number of packet losses due to errors in low levels, that is in physical and link layers, which allows transport protocols like TCP to grow their window of outstanding data sent to the network up to the pipe capacity and filling router queues until some of the queues in some of the routers overfills and causes packet drop. So throughput is now mostly limited by the way that transport protocol congestion algorithms react to losses due to router queue overflows. What does it mean for performance monitoring? I think that we can say that the networks are on the verge of over-provisioning, which is roughly defined as the network being loaded to about 10% or so, which is the network known to behave nicely in terms of low and stable delay and low packet loss. And I think that it will probably remain so for some foreseeable future because the volume of traffic is increasing, the capacity of installed network is also increasing, but I think that it is likely that we will not go beyond 10 gigabits per second on one pass in near future. Rather, we will go to using parallel paths. So I think that in order to understand behavior of network and behavior experienced by traffic in detail, we need to monitor network closely in short time scales. And this monitoring must work at high speeds. And how can we achieve that? There are three primary ways of performance monitoring. First, we can gather and process data acquired from network components like routers and switches. Second, we can do active monitoring by injecting test packets into the network and analyzing them as they are received somewhere else in the network. And finally, we can do passive monitoring. When we do not inject anything into the network, we just observe the existing user traffic which is there. I think that each of these methods has its advantages and shortcomings, and that a comprehensive monitoring system should use some balanced combinations of them. So let's look at these methods at a little bit more detail. Data from network components are mainly represented by statistics in counters maintained by routers, which can be read by Snmp, and flow records generated by routers. The good thing about this information source is that we have information about each particular link in the network, and we do not need to install any probes in the network. So it has very good space granularity. The problem with statistic counters is that routers tend to update them with some delay when they do not have something more important to do. So we can't really get short timescale information by reading statistics from routers. And the problem with flow records is that they are not completely reliable. Sometimes they are simply not sent by routers due to either temporary congestion or due to possible bugs in software which are exposed particularly when we combine some features like IPv6 and multicast together and so on. To illustrate the problem with Snmp counters, this picture shows load on some of the links in our network computed from 60-second samples of interface bind counters. You can see some fluctuations there, and we may be interested in a finer view to check how big the peaks really are. Unfortunately, when we read the interface bind counters, say once per second, we get a picture which is distorted by artifacts caused by delayed update of interface byte counters. We can't get to finer time scale than about 10 seconds in this way. As for active monitoring, it's surely the easiest way to monitor one-way delay and jitter. We just send test packets and subtract sending time from the reception time. Just the clocks need to be synchronized, but it's not a problem with GPS receivers. And certainly, active monitoring can also provide a definite answer that we can pass some high data rates through the network using heavyweight tools like iPerf. When we need to check round-trip time, we can send ping to some host, but we need to send it to a responsive host which responds in real time, which is unfortunately not the case of routers, which again tend to respond to both ICMP and UDP pings with some unpredictable delay, which is a pity, because if that worked, we could use ping to routers along a network path to check for increasing or fluctuating round-trip time to some router, which may imply increasing or fluctuating queue in that router. Of course, heavyweight throughput measurement by iPerf and similar utilities stresses existing elastic traffic on the network, which is both harmful for the user traffic and it implies that what we measure may not be exactly the available bandwidth which is on the network. The passive monitoring has two primary advantages over active monitoring. That is, it observes properties experienced by the real user traffic rather than properties experienced by some testing packets, which may be different. And second, it is non-intrusive, because when we do not send anything into the network, then we do not influence user traffic in any way. The problem is that when we want to monitor high-speed links passively, we need to deal with high-speed data rates, and that might be compute intensive. And for that reason, the Snmp project started 2 years ago, which concentrates on passive monitoring and has two goals. The first is it should overcome the gap between the speed of PC CPUs and the speed of network links by shifting monitoring functionality down to programmable monitoring adapter being developed in the project, so that up to the PC only results are passed. And second, it should allow for easy writing of portable monitoring applications by providing MAPI or monitoring API. There were already 2 presentations about the Snmp project yesterday, which covered these 2 goals, so I don't need to go into detail. Instead, I would like to mention that as part of the project, we are developing a couple of monitoring applications. From those, I would like to say a little bit more about QoS monitoring. Currently, we can monitor passively short timescale link load, one-way delay, and packet loss rate. In this picture, you can see example of link utilization monitored passively and computed for 10 millisecond averages, which would not be possible to do by reading byte counters using Snmp. In this particular case, the link load was dominated by one TCP bulk transfer, which saturated the link and which caused route to queue overflow at particular times, resulting in a slow start and in a reduce of link utilization that are these drops here. And perhaps the most interesting characteristic from the monitoring point of view is packet loss rate. A popular way to try to measure packet loss rate is by active monitoring, when we send test packets into the network and count how many of them do not arrive to some other point in the network. The problem is how many of these test packets should be sent, because let's say that we send 100 test packets per second for point-to-point measurement. If you want to do continuous full mesh measurement between a couple of points, that would imply really a lot of packets sent to the network, which may influence the load of links and routers. On the other hand, these 100 test packets per second would still imply that we would need 10,000 seconds or about 3 hours to detect packet loss at the magnitude of 10 to minus 6, which is a common range in current networks. So it is quite difficult to get short timescale information about low packet loss rates using active monitoring. So what can be a possible solution? We can try to use counters maintained by routers counting losses due to queue overflows. In this way, we would miss losses caused by lower layer faults, but I said that these are not so important, so that it would not be a problem. The problem is that in modern routers, there are sometimes several queues and several places where packets could be lost, and thus routers maintain several different counters in their MIB, which we would have to inspect and combine to get information about number of packets lost in the router, and these counters are proprietary for different router types. So it's quite a difficult method. I think that the most promising method is to use passive monitoring when we capture packets coming to the network and going out of the network on the border points. This is actually the way that Sprint uses in their network, but they do that offline. That is, they capture traffic using DAC cards, store dumps of packet headers on hard disks, After that, they remove hard disks from computers, send them to supercomputing center and process them afterwards. I think that using smart monitoring cards like the Snmp adapter, which can do statistics and possibly sampling on the card itself, we can do this analysis in real time. And this is what we are working on right now. We have some preliminary results that show promising correspondence between numbers indicated by passive monitoring and what might be a real packet loss there. It shows that we can also use sampling, that is, we do not need to capture all packets, but of course sampling reduces precision. So the conclusion is that in order to understand network behavior in detail, we need to do short timescale monitoring, and to do that passive monitoring usually provides more realistic results than active monitoring. And passive monitoring at high speeds require hardware support built in monitoring adapters, so that we do not have to move large volume of data and process it in host CPU. And that's it. So thank you for your attention.
Okay, thank you very much. Sorry, are there questions? The interfaces, I think, what's the speed? Is it 1 or 10 gigabit what you're now doing?
Speed at speed.
That you can measure it with your this Snmp equipment.
Currently, we have 1 gigabit monitoring adapter up and running, and we can use it to monitor the network. And 10 gigabit adapter is in development. The hardware itself is already developed, it exists, and firmware support and the driver for that is being developed.
Okay. I didn't see the Snmp meetings yesterday or this morning. Are they also going to being put in other places, or only in Europe, or are they? What is the distribution of these passive boxes?
Yes, of course, there are few partners who are interested in using Snmp adapters, and we have more plans for exploitation of that, because I think that it's an interesting approach to performance monitoring.
Other questions? No. Then I want to thank him again, and everybody else who was here. Thank you. Before you leave, I think it's important to know that the buses will leave at, let's say, in 12 minutes or something like that. So that's earlier as in the other days. So remember that, otherwise you can't prepare properly for the beach party, of course. So have fun over there, and see you. Bye-bye.